chemistry time. Let's talk about the periodic table and the periodic table. The periodic table. This is going to be brief. We're going to talk about some basics that is, if not is, then definitely be review from physical science, and we're going to talk about some trends in the periodic table which are new to you, but are not, in my opinion, complicated. I would say maybe the intricacies of it would be complicated, but we're going to touch on it at a surface level that shouldn't be overpowering to your little pubescent brains. Okay, well, what should we do first? Well, let's draw the periodic table and the periodic table. Does someone want to explain the joke to the camera so that the two viewers can understand what's going on here, our inside joke? The two viewers that are also you, but for posterity. What is the joke? Hold on, I'm going to interview Kyla. This is the interview mic too.
Because I accidentally wrote the periodic table and the periodic table, and it was supposed to be the periodic table and the periodic theory.
And then you also, even when you corrected it, you didn't quite get it. Okay, that's good. That's good. Also, I lost this used to have a pop filter on it. You'll pop, so that when I make this sound like pop, my spit doesn't go in there and make it sound bad. But then I lost it. I have no idea where it is. Maybe I'll find it when I take off my garments tonight, because that might be where it's trapped. Anyway, the periodic table. This is what it looks like. It doesn't usually have an eraser in the middle of it, but right now it does. Okay. Let's name the things. The first part we're going to do, this is going to be entirely diagram based. I would label, one of the reasons I had you do your bell work the way I had you do it is so that you can already have a head start on this, and when you go to label these things, you can change them if they're wrong, which they shouldn't be, but for the most part you should just be right. What's this first group called? First of all, what is a group? A column. A verb called a group, or family. Called a family. What's true of your family?
They're all similar.
They're all similar, yeah. The same. You don't behave exactly the same. But you look similarly enough that you are a family. It's the same way with the elements. Is it just about the looks for the elements, though? No, they have similar properties. For instance, my boy Mitch and my boy Natalie, they have the exact same hair. Almost, in fact, everything about them is almost exactly the same. Much like all of these. What are these? What is this family called? I didn't mean to draw that horizontally. Yeah, it might as well be called the berries. No, what is it, though? Alkali metals. Hold up. Yeah, that's fine. Hold up. Why do they have similar properties? What else is true about the alkali metals?
They need to lose
Peyton says that they need to lose an electron. They have one valence electron. They have one valence electron, so that contributes to their properties. Their properties are those of an atom, which have one valence electron. What might an atom that has one valence electron have as some of its properties? Very reactive, because it's pretty close to having an ideal number of valence electrons, and so they react very readily. What's the next group called? Alkaline earth metals. What are all these boys called? 3 through 12. Transition metals. Let's see, we got 3, 4, 5, 6, 7, 8. What are these ones called down here?
Actinide series.
Yeah, the intertransition metals. Yeah, and then separately they're called actinide and lanthanide. Mm-hmm. And these things go, all of them, these two series get shoved in right here. Really, the correct way to draw the periodic table would actually be like this. We're going to talk about why we don't in a second here. The correct way to draw it would be like this, with the intertransition metals down here. Why don't we do that usually? There's a lot of empty, wasted space here, and it makes the aspect ratio kind of weird. So if we're trying to put this on a poster, it's just easier if we grab that all out and put it on the bottom. It's kind of become customary, but that is where they go. Why? Why do they go there? Well, let's draw on this one. What's this block called? Well, they not the bottom ones. Yeah, but the lanthanide series is not. And also I have actinide and lanthanide switched around, so pretend I didn't do that. But what is true about these? This little group here, these pink ones I just colored in. What's true about all of them? Yes, they're metal. Actually, no, not hydrogen.
Oh, I got it. They're light metal.
No, not hydrogen. What is true about all of them, though? They're in the what? I'll give you a hint. They're the S block. The S block. What does that mean? Yeah, their electron configuration ends in S's. Ooh, that was pretty close. What I call these ones? What I call these ones? Mm-mm. Are you trying to spell something? S-H? P block. P block. The P block. What are these ones here? Oh, let me get a different color out. What are these ones here? No. The D block. They really should be quite a bit shorter than that. And then what about F block? Thanks, Mitch. Anyway, we got kind of sidetracked from our main goal, which is, now what do I call these ones? Usually we just call these group 3, or group 13, or group 3A, maybe group 3B. I don't remember exactly because that's the old naming scheme. Sometimes we also call them icosagens. That's very seldomly used. Probably just group 3 would be adequate, or group 3A. These ones, group 4, are called the Christalogens, or group 4. The group 4 is going to be a lot more common. And actually, the more common is 13 for the icosagens, 14 for the Christalogens, and then 15 is called the Nictogens with a silent P at the beginning, which is called 5A, or 15. And then you probably know these last 3. What's this one? Group 16 are you remember these? Nope, never mind. Chalcogens, which are group 6A, or group 16. You do remember these, I know you do. Someone has to, or I will quit. Thank you, Lily. The halogens, which are group 7A, or 17. And then everyone knows these. Thanks. The noble gases. Noble gases got to buzz in. 8A, or group 18. All of these things that I've labeled this one up here with are what? What have I labeled all this with? These are all the different what's at the periodic table? Groups. They're all the different groups of the periodic table. And why does it look like this? Why not just make it a grid or like a stack of cards? Or it is like this for a reason, and that's good enough. No, the reason though. Why is it like this? What's the benefit of having them like this? What does this allow us to show? Well, once again, what's true about all these? Because they all have similar properties because they all have the same number of valence electrons. So basically, we order them in order of valence electrons. How many valence electrons here? 1. Here? 3, 4, 5. How many? 2. But they can behave differently because they can bond with their inner ones.
What's the name?
And these are Nictogens. Anyway, here's what I got. This is a three-dimensional way. Oh, I really shoved it in his face. This is a three-dimensional way of representing the periodic table. And what it is I'm going to pass this around too so that my in-person boys can see it. But okay, I'm having a hard time actually making this look good. Okay, there we go. It's three-dimensional, and what it has done, go back over there. What it does is it loops around. So like hydrogen up here, all by itself has one color. It's yellowish, and it's because this can behave in a way that it can hydrogen can gain or lose 1 electron. It only has 1 electron. If it gains 1, it'll have 2 like helium. It'll be happy. If it loses 1, it'll be less happy. But it just whatever. It's happier as an ion in either direction. Then the next period What's a period? Row. It's a row. And why is it called that? What's a period? I mean, in general, what's a period? Okay, it's a punctuation mark. It's the end of the sentence that is related to its other meaning. What is a period? Sure, yeah, it's related to it. It's a time. It's a cyclical thing. In a wave, a period is the time it takes for one wave to pass. In magazines, a periodical is a magazine that's issued every month or 3 months or 6 months or whatever, but it has a periodicity. It has a certain regularity to it. That's why it's called a period. In the period of these, they have a regularity. The first period goes 1 valence electron, 2 valence electron. Okay? The second period goes 1, 2, 3, 4, 5, 6, 7, 8 valence electrons in that order. The third period goes 1, 2, 3, 4, 5, 6, 7, 8 valence electrons in that order. The fourth period goes 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 3, 4, 5, 6, 7, 8 valence electrons in that order. It's periodic. That's why it's called the dadgum periodic table. And that's why this guy is important. I don't know. Look at that. Mitch?
Okay, I have a question.
Okay, what's your question, Kylo? Well, hold on. Let me come interview you.
What's that word?
Oh, no, this is not the kind of question I want to hear. What? Okay, halogens. Chalcogens. Chalcogens, like they generate chalk. Halogens generate salts. Chalcogens generate. No, that's not stupid, but you're also wrong. Chalcogens. Chalcogens. Okay, so here are some trends, and this is the final thing we're going to talk about. There is more in your chapter how will you know what else is in the chapter that we aren't talking about? I've been over this before. You're going to read it and you're going to do your chapter review, and that's going to lead you to the correct knowledge. Here are some periodic trends in the periodic table. As we go down a group, for instance, this group, as we go down the group, what happens to the size of the atom? Yeah, atom size bigger. Why? There's just more charge. So that adds, really, comparing hydrogen to the next one down, lithium, to the next one down, sodium, they have a whole other energy level, a whole new principal energy level to fill. So they get bigger. What about now going across a period? What happens to the atom size? Do they add a whole new energy level? No. What does happen? They add more protons and neutrons and more electrons. And so what happens with the strength of the attraction? It gets bigger strength of attraction, so they actually get what going across a period?
Stronger.
Yes, and therefore the atom gets... Okay, try again. There's only two choices, smaller or bigger, so which is it? It's smaller because they get more and more attracted. So there's no more principal energy levels, but going across a period, the atom size gets smaller going across a period. So going down a group, the atom size gets bigger because it adds new energy levels. And going across a period, the atom size gets smaller because there's more electromagnetic attraction. Neat. The next thing we talk about for trends is ionization. Do you have a definition of ionization energy in your vocab? Someone's going to find one. Camden's going to find one, and I'm going to make her say it into the microphone. Define ionization energy, Camden.
The energy required to remove an electron from a gaseous atom generally increases in moving from left to right across a period and decreasing in moving down a group.
Okay, I know that was her. Yeah, she told us how it goes. But let's define it first. Let's redefine it. Ionization energy is the energy it takes. What is energy basically? We talked about this in physics. We talk about this all the time in science. What is energy basically? On the most basic level, not always. No, not always. What is energy basic? The very most basic level. Energy is the ability to do what?
React.
Yes, thank you, Lily. Cause change. Energy is the ability to cause change. Jot that down somewhere, because that is the fundamental principle of the entire universe. Energy is the ability to cause change. That is the most fundamental thing about the entire universe. So the energy, the amount of change that has to be caused to remove one electron is called the ionization energy.
So what's your definition?
Oh, your definition was fine before, but this is what I said was the amount of energy it takes, to remove one electron first electron is called the first ionization energy. Do you think it's high or big for these? How much energy do you think it takes to remove one electron from these that have one electron, one valence electron? Not a lot, because they really want to get rid of it. Remember, they're more satisfied if they can meet the octet rule. So looking at, for instance, this guy, what is he? Rubidium. Rubidium, which has one valence electron, it would be much, 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 much more stable if it had the same electron configuration as krypton, clear over here. And so it barely takes any energy at all to remove that one electron. So it has a very low first ionization energy. Why am I saying first ionization energy? Because we're talking about how to remove the first valence electron. So these have a very low ionization energy. So what happens as we go across a period? Yeah, greater first ionization energy. What about down a row? Well, let's think about it this way. Hydrogen, just like with our atomic size, what's happening as we go down a group? From hydrogen to francium, what happens when we go down this group? The electrons are getting, there's more of them, but also they're getting what? Think about a valence electron of hydrogen compared to a valence electron, the valence electron of hydrogen, compared to the valence electron of francium. What's true about it? Yeah, francium is much, much further away. So do you think francium has a higher or a lower first ionization energy compared to hydrogen? Has a lower one. It's easier for francium to get rid of its one valence electron than it is for hydrogen because it's further away. Basically, think of it like this. It's further away from the nucleus, and so it's harder for the nucleus to exert the pull that is required to hold on to that valence electron. So atom size gets bigger, but also there's a lower first ionization energy going down. Your book also talks about second ionization energy. There's such a thing as third ionization energy, all the way up to eighth ionization energy. But this is the one that has the most simple and the most easy to explain periodicity. So that's the one. Yep, so as we go down a group, there's a lower first ionization energy. And then the final thing we talk about for periodicity is electronegativity. Electronegativity. This one is a lot more frequently used later on in the book and later on in chemistry than ionization energy. It's almost like the exact opposite of ionization energy. Where ionization energy was how hard it is to remove an electron, electronegativity is how badly, let's put this, how energetically, try to spell one thing right in our entire life, energetically, an atom tries to gain an electron. So where would this be the highest? Which atom wants the electrons the most? Very good, Lily. The ones on the right of the periodic table, which I think you were talking about, but you said left, Mitch. But Lily's right, the halogens. Why not helium? Helium's way up here. Why not him? Yeah, it's already has it. This is already satisfied. The noble gases don't apply to any of this because they're already satisfied. They don't react. Both of these things you're talking about, ionization energy and electronegativity, talk about reactions. The noble gases don't react, or not never, but in this case they don't react. We're not talking about that right now. So fluorine has the highest electronegativity. It wants electrons the most. Why? Why does it want electrons more than astatine, for instance? Well, it's the same exact reason as the hydrogen thing. Well, it's actually almost the exact opposite reason. Francium has a lower first ionization energy than hydrogen because it's farther away. Well, fluorine wants an electron more because the electrons are all closer to the nucleus. The electrons are pulled more closely because they're nearer to the nucleus. So fluorine has the highest electronegativity. What probably has the lowest electronegativity? What thing on the periodic table wants an electron the least bad? Well, let's think of a trend. The fluorine. So what did we just say about fluorine compared to astatine? So what's the trend for electronegativity going down a group? Yeah, so lower electronegativity going down a group. Electronegativity. Going down a group, lower electronegativity. And what about across a period? Well, we said fluorine's the highest, so what happens when we go across a period? From left to right. We said fluorine has the highest electronegativity. It wants electrons the most. So as we go from left to right across the period, what must be happening? Yeah, higher electronegativity. So if top right, that is to say fluorine, has the highest electronegativity, what probably has the lowest electronegativity? Could you go lower than calcium? How low can you go? Can you go down low? All the way to the flow? Francium. Francium has electronegativity. Yep. So francium is on the very left bottommost, right? Electronegativity increases as we go up. I shouldn't have said it like that. I should have said the electronegativity decreases as we go down, and it increases as we go from left to right. So it follows that bottom left. But all of this is just a product of, remember, we could arrange these. This is all a human construction. The elements are real, but the way we organize it is all a construction. The reason I think this is, if not the pinnacle, then the most common pinnacle of human achievement, of human organizational thinking. This is a triumph of human organizational thinking. I truly think, even though let's assume that there are millions of aliens in the galaxy, okay? Millions of different civilizations. I really think that they would generate something like this to describe the elements, because it just flows so neatly. It organizes in so many different ways. When Mendeleev set up this table, he didn't intend to have electronegativity go like this. It just did, because it flows forth from the way it's organized. We could just as easily have it in a grid. We could have it in a list alphabetically like Lavoisier did. It'd work fine for most things. But having it organized like the periodic table in this shape helps us understand so many more things about it, right? Just like I said, this is a human construct. There's nothing about this that is a physical part of the universe. It just so happens that the way we organize it has all of this scribbling jottings down that Mr. Keim did all afternoon. All of that comes just from the shape of. What about you, Kyla? Do you have questions? Okay, well then bye.